1930. Bavaria is on the brink. Factories are closing, and the Great Depression is strangling the economy. But on the farms, progress has hit a wall. Farmers, they refuse to change. To them, a combustion engine is a noisy foreign threat. They trust only the horse, and they believe no machine can ever replace a living partner. Yet, in a soot-filled workshop in Marktoberdorf, a quiet experiment begins. A machine with just 6 horsepower and a masterful psychological name, the Dieselross. A diesel horse designed to trick the mind and rewrite the rules of farming forever. From that small forge, a dynasty would rise, one that didn't just survive the collapse, but engineered the most expensive machines on Earth. And that company? Fendt. In 1930, if you walked into Johann Georg Fendt's operation in Marktoberdorf, you wouldn't find a sprawling industrial complex or a humming assembly line. You would find yourself in the thick, choking atmosphere of a traditional Bavarian blacksmith shop. The air was heavy with soot, and the soundtrack was the rhythmic striking of hammers against anvils, not the automated hiss of hydraulics. This was a workshop, not a factory, and it was operating in the shadow of the Great Depression. The economic landscape was bleak, and survival was the only metric that mattered. Johann Georg Fendt and his sons were working on a machine that would eventually define their legacy, but at the time it barely resembled what you might call a tractor. It was essentially a mechanized mower, powered by a small 6-horsepower engine. This wasn't a monster designed to pull massive plows across the American plains. It was a humble tool, built to do the work of a single animal. But the Fendt family knew that engineering alone wasn't enough to change the minds of the deeply conservative Bavarian farmers. These were men who had farmed with horses for generations. To them, a combustion engine was noisy, complicated, and foreign. It was a threat to their entire way of life. This is where a masterful piece of psychological branding came into play. A local brewery owner and friend of the family named Franz Josef Zeiler stepped in with an idea that bridged the gap between the past and the future. He suggested naming this new machine the Dieselross. In German, it literally translates to diesel horse. This wasn't just a catchy label, it was a calculated strategy to reframe the technology. By calling it a horse, Fendt positioned the machine not as a replacement for the farmer's skill, but as a tireless evolution of their most trusted partner. The pitch was simple, but devastatingly effective. This horse didn't need to sleep, it didn't need to be fed when it wasn't working, and it ran on efficient diesel rather than oats. It alleviated the anxiety of adoption, presenting the tractor as a trusted stablemate rather than an industrial invader. However, the quiet revolution of the Dieselross ran headlong into the chaotic reality of global conflict. With the onset of World War II, the German economy was refactored entirely for the war effort. Due to severe shortages of raw materials, the government imposed a strict ban on liquid fuel tractors for civilian use. Diesel was for tanks and submarines, not for plowing fields in Bavaria. For most manufacturers, a ban on their primary fuel source would have been a death sentence. The assembly lines should have stopped. But Fendt did what they would continue to do for the next century. They engineered their way out of a dead end. Facing a total lack of petrol, the company undertook a radical pivot to Holzgas, or wood gas technology. The result was the G25 model, a tractor that looked like a science experiment gone wrong. To bypass the fuel ban, engineers attached a massive Einbert-style gasifier directly to the chassis. This was a cylindrical furnace that turned the tractor into a mobile power plant, burning wood chips to generate a combustible gas that could run the engine. It was a testament to agility under pressure, but for the farmer, it was a daily battle against physics. Operating a G25 was nothing like turning the key on a modern diesel engine. The process was arduous and physically demanding. Before you could even think about moving the tractor, you faced a preparation ritual that lasted anywhere from 15 to 30 minutes. The system required precise fuel management. The wood had to be cut into small blocks measuring exactly 7 centimeters and required dry storage with a preferred moisture content of 15% or less for optimal gas production. You had to load the hopper, light the fire, and then manually operate a hand crank blower to stoke the flames until the gas was rich enough to fire the cylinders. It transformed the driver from a tractor operator into a locomotive stoker. The experience of driving the G25 was equally gritty. The system was inherently messy. The combustion process produced a thick, sticky tar that clogged filters and required daily cleaning. Drivers were constantly surrounded by the smell of burning wood and the looming threat of carbon monoxide. On top of that, the conversion to wood gas came with a significant penalty in performance. The base engine block was rated for 25 horsepower, but when choked by the inefficiencies of wood gas, it could only deliver 15 to 18 horsepower. It was weaker, dirtier, and harder to use than its diesel predecessor. But it ran. Between 1942 and 1949, Fendt produced exactly 1,497 of these wood-burning survival machines. In a time when major industrial centers were being targeted and supply chains had collapsed, these tractors kept the farms running. They ensured that food production didn't grind to a halt when the diesel pumps ran dry. This era forged a distinct identity for the company. While other manufacturers relied on brute force and abundance, Fendt learned to survive on precision and adaptability. They proved that even when the resources were stripped away, the right engineering could keep the wheels turning. But as the war ended and the economy began to accelerate, a new problem emerged. The farmhands were leaving for the factories, and the farmers left behind would need a machine that could do the work of an entire crew. By the 1950s, West Germany entered the Wirtschaftswunder, or economic miracle. But for the farmer, this miracle was a curse. The factories in Stuttgart and Munich began offering wages that agriculture couldn't match, drawing the rural workforce into the cities. You can see the crisis in the archival texts of the time, where farmers lamented that hired hands were developing into critics or simply leaving. The traditional farm, which relied on teams of laborers, was collapsing. The farmer was suddenly alone. Fendt responded in 1953 with a machine that looked like nothing before it. The F12 GT. This was the era of systems engineering. The GT, or Gerätetrager, tool carrier, was a radical departure from the tractor silhouette people knew. It looked like a steel skeleton. The engineers moved the engine from the nose to a position under the driver's seat and later behind the axle, creating an open architecture that exposed the ground beneath. The defining feature was the Zentralholm, or central spar. This was a single high-mounted box section beam connecting the axles. It turned the tractor into a self-propelled platform truck. This allowed a specific type of magic. A single operator could mount tools in the front, the middle, and the rear simultaneously. Because the mid-mounted tools followed the front axle's trajectory, the design offered a perfect view of the implement. A farmer could cultivate beet rows with centimeter-level precision without ever turning around. It allowed one man to do the work of three. Fendt branded this the Einmann system, or one-man system. It was a machine of liberation. It allowed the farmer to transport milk churns on the front platform and hoe crops in the middle, effectively eliminating the need for the horse-drawn cart and the vanished farmhand. The DLG, German Agricultural Society, awarded this system a gold medal in 1959. This wasn't just a prize for mechanical performance, it was a recognition of the system's ingenuity in addressing the operational needs of the modern farm during a critical labor shortage. It didn't just plow fields, it saved the family farm model. The engineering team didn't stop at versatility. They soon tackled the physical toll of driving. In 1968, they introduced the turbomatic fluid coupling. Up until this point, driving a tractor meant wrestling with a heavy, jerky mechanical clutch that wore out the driver's left knee and machine's gears. The turbomatic changed the physics of the connection. The system placed a hydrodynamic coupling between the engine crankshaft and the clutch. Inside a donut-shaped housing filled with oil, a pump wheel connected to the engine faced a turbine wheel connected to the transmission. There was no mechanical contact. Power was transmitted solely by the mass and velocity of the oil throwing itself against the turbine blades. This fluid cushion absorbed the violent shocks of a diesel engine, dampening the vibration that rattled the driver's bones. But the real breakthrough for the operator was the standstill feature. On the steep slopes of the Alps, a driver could hold the tractor stationary using only the throttle without touching the brakes or the clutch. It operated almost like an automatic car. For farmers doing front-loader work, constantly starting and stopping, this was a revelation. User reports from the era frequently praised it as a knee saver. This willingness to add cost and complexity to save the driver from pain earned Fendt the reputation as the Mercedes of tractors. They had proved they could build the most versatile and comfortable machines on the market. However, comfort and agility were about to face a new challenger. Across the Atlantic, American manufacturers were building machines focused on raw horsepower. forcing Fendt to enter a race where speed would become the ultimate trap. In the 1970s, American manufacturers arrived in Europe with machines focused on raw horsepower, forcing Fendt to fight a two-front war. To survive, the company had to defend its home turf against these high-horsepower invaders. They deployed the mass-market Farmer 300 series to pay the bills, but the real counterattack was the flagship Favorit 600 LS. This machine was designed specifically to stand toe-to-toe with the massive imports arriving from across the Atlantic. It was a period that stretched through the 1980s, often remembered as the golden era of mechanical engineering, giving us the Favorit 500 and the 800 TurboShift models. These square tractors have since become cult classics, introducing features like the Rufa, a reverse drive station that allowed the seat and controls to spin 180 degrees. But beneath the steel and paint, the engineers were hitting a wall. The industry was trapped in a cycle of adding more and more gears to manage speed and torque. By the time the Favorit 800 TurboShift arrived, the engineering complexity had spiraled out of control. Through its complex ZF transmission system, the tractor featured a staggering 44 distinct gears. It was becoming unmanageable. Drivers were exhausted, constantly wrestling levers to find the right ratio for the terrain. The engineering reality was undeniable. Stepped gearboxes, no matter how complex, caused significant efficiency losses. Every time a driver shifted gears under a load, they suffered a torque interruption. The tractor lost momentum, and the engine was almost never operating at its peak efficiency for the ground speed. It was a constant, wasteful trade-off. Manufacturers tried to patch this by adding power shift stages, but this just made the transmissions heavier and more complex without solving the core physics problem. Hans Marshall, a lead engineer at Fendt, looked at this speed trap and realized the industry was wrong. Adding more gears wasn't the solution, it was the problem. He knew they needed to eliminate the gears entirely to achieve optimal performance. The theoretical answer was a CVT, or continuously variable transmission. The concept existed. Early hydrostatic drives offered stepless speed control, which is exactly what Marshall wanted. You see these systems on lawnmowers and combine harvesters, using a pump to push fluid to a motor. But for a heavy-duty tractor, they were a disaster. When you pushed a purely hydrostatic system to pull a heavy plow, it would lose up to 40% of the engine's power just generating heat. It was inefficient and weak. This was the crossroads. On one hand, you had the mechanical gearbox, efficient but clunky and limited. On the other, the hydrostatic drive, smooth but wasteful. The company treasury, and arguably the future of independent German tractor manufacturing, rested on solving this riddle. The engineers decided to stop refining the past and start building something that seemed impossible. They weren't just going to design a new gearbox, they were going to bet the entire company on a transmission that didn't technically exist. In the early 90s, that gamble materialized as Project Vario. The timing could not have been worse. The agricultural machinery market was in a freefall, and the company was burning through its reserves. Yet, in a move that terrified the accountants, management authorized a development budget estimated at 100 million Deutschmarks. It was an all-in move during the company's most precarious period. Hans Marshall, the head of the advanced development, wasn't just building a new component. He was attempting to merge two opposing forces of physics: mechanical efficiency and hydrostatic control. The solution was a concept known as power splitting. Using a prototype called the Tristat, the system utilized the planetary gear set to divide the engine's torque into two distinct paths. The first path was mechanical, providing the raw efficiency needed for heavy pulling without the heat loss of a fluid drive. The second path was hydrostatic, using a hydraulic pump to offer infinite precise control over speed. Think of it like this. A standard transmission is like a staircase. To go higher, you have to jump from one step to the next, losing momentum every time. The Vario is a ramp. Because of how these two paths reunite at a summating shaft, you can slide from a dead stop to 50 kilometers per hour without a single gear shift. It keeps the engine at its absolute sweet spot, regardless of the ground speed. However, making this concept work in the real world required machining precision that bordered on the impossible. To achieve the necessary speed range and efficiency, the team had to engineer a hydrostatic pump with a massive 45-degree swing angle. This was uncharted territory for hydraulic engineering. Skeptics inside and outside the industry dismissed the project as a fantasy. They predicted the complex system would fail under the brutal loads of plowing, or that the cost would bankrupt the family business before a single unit was sold. But the engineers persisted, driven by the knowledge that if this failed, there would be no company left to save. When the curtain fell at Agritechnica in 1995, the Favorite 926 Vario silenced the room. It didn't just look different, it looked like it had landed from the future. With its sharp-edged hood, striking green side panels, and a panoramic cab that offered unprecedented visibility, it stood apart from the utilitarian blocks of the competition. But the real shock was inside the cab. The forest of levers that defined tractor driving for decades was gone. In its place sat a single joystick. The 926 Vario became an instant sensation, drawing massive crowds and stunning the trade press. It was the first high-horsepower tractor that didn't force a compromise between torque and speed, proving that a CVT could handle the heavy draft work of a large farm. However, the financial weight of this moonshot project had taken its toll. In 1997, the family made the difficult decision to sell the company to the American corporation AGCO. While fears of a hostile takeover and the loss of German identity loomed, the acquisition proved to be the catalyst the brand needed. It provided the massive injection of capital required to industrialize the Vario technology globally. The gamble had paid off, securing the brand's survival and setting a new standard for mechanical efficiency. But as the gears disappeared, a new complexity was beginning to emerge, one that wasn't driven by hydraulics, but by data. By the turn of the millennium, the definition of a tractor began to shift. The machine was no longer just a collection of gears, pistons, and hydraulic fluid. It was becoming a rolling server rack. The introduction of the Fendt 926 Vario had already replaced the traditional forest of gear sticks with a single joystick, or Fahrhabel. This fundamentally altered the human-machine interface and the physics demands placed on the driver, moving the industry toward a system that was intuitive rather than labor-intensive. But hardware was only half the equation. The iron was ready, but it needed a brain. This shift to a joystick control system didn't happen without friction. In the early 2000s, a distinct cultural divide formed in the farming community. This new interface was met with deep skepticism from traditionalists. These were operators who had spent decades wrestling with clutches and levers, and they viewed this effortless control with disdain. The argument was bitter. To the old guard, a callus on your hand was a badge of honor. If you weren't fighting the machine, you weren't working, you were just riding. They didn't just call it new technology, they called it cheating. They feared the new generation would become lazy drivers. However, this resistance overlooked the brutal reality of spending 12 to 16 hours a day in a cabin. The narrative of the lazy Fendt driver was often perpetuated by owners of rival brands, but the reality for the operator was quite different. The technology didn't remove the skill, it removed the fatigue. Freed from the cognitive load of constantly managing engine speed and transmission ratios, the operator could finally focus on the implement, the field conditions, and the actual business of farming. Fendt had realized that a tired driver is an expensive liability, while a fresh driver is an asset. To fully exploit this new ease of operation, the engineers introduced the TMS, Tractor Management System, in 2004. This was the moment the tractor truly became a computer. The system integrated the engine control unit and the transmission control unit via the CAN bus system, allowing them to communicate and coordinate without direct human intervention. Before this, a driver had to manually balance the throttle and the gear ratio to find the sweet spot. Now the machine did the thinking. The driver simply commanded a target, such as the ground speed of 50 kilometers per hour. The software then took over, controlling both the engine and the transmission to achieve that target at the most efficient operating point possible. It automatically adjusted engine speed and transmission ratios to maintain velocity while minimizing fuel consumption. It was a significant departure from the manual adjustments required in earlier models, effectively placing a master engineer inside the gearbox to make thousands of micro decisions every minute. The industry demanded proof that this complexity was worth the cost. That proof arrived when Profi International Magazine, a respected authority in agricultural machinery, conducted rigorous tests. The data confirmed what the engineers of Mark Toberdorf already knew. The TMS system could deliver fuel savings of 10 to 15% compared to manual operation or competitor machines in specific applications. Over the life of a machine running thousands of hours, that percentage translated into a massive financial advantage. This efficiency gain became the primary defense for the brand's notorious pricing strategy. The Fendt 900 Vario TMS commanded a green premium of 20 to 30% over comparable models from giants like John Deere or New Holland. In the industry, this became known as the Fendt tax. For many farmers, that upfront cost was a bitter pill to swallow. yet the economics were sound. The long-term benefits of fuel efficiency, reduced maintenance, and increased productivity often offset the initial expense. You weren't just buying a tractor, you were buying a lower total cost of ownership. However, even the most disciplined engineers have moments of hubris. While the TMS was conquering the market through logic and efficiency, Fendt decided to see how far they could push the laws of physics with the Tresix. This was a prototype that looked less like a tractor and more like a lunar rover. It was a six-wheeled monster powered by an MAN D2676 V8 diesel engine producing 540 horsepower. To manage that massive output without tearing itself apart, it utilized two independent Virio transmissions. It was an experiment in absolute power designed to provide massive traction without the soil compaction issues of a tracked vehicle. The Tresix was a spectacle. It featured 3 axles and a level of complexity that bordered on the absurd. But unlike the Virio, the market didn't embrace the monster. It was too complex, too large, and perhaps too far ahead of what the infrastructure could support. It never entered mass production. But in the grand scheme of Fendt's history, the failure of the Tresix was just as valuable as the success of the TMS. It reframed the company's approach to innovation. The project proved that the engineers were willing to try the impossible, even if it meant failing publicly. It taught them the limits of a multi-axle system and how to manage extreme horsepower. They learned that building a bigger beast wasn't the answer. The answer lay in applying that high horsepower capability to a standard user-friendly frame. The ridicule regarding the lazy driver had faded, replaced by a quiet respect for a machine that could pay for itself. Fendt had mastered the software and the transmission. Now they took the hard-won lessons from the six-wheeled monster and prepared to distill them into a masterpiece of conventional engineering. By 2015, the global agricultural market was shifting toward massive horsepower, but Fendt chose not to follow the crowd with articulated bend-in-the-middle steers or track behemoths. Instead, they launched the 1000 Virio. This machine looked like a conventional tractor, but it hid a complete reimagining of how power is delivered to the ground. This wasn't merely an upgrade, it was a calibrated strike against the inefficiencies of high-horsepower farming. Taking the lessons from their past experiments, they aimed to dismantle the articulated market with a rigid frame design that could handle over 500 horsepower without tearing up the heavy soil it was meant to protect. At the core of this masterpiece was the Fendt ID low engine speed concept. If you've ever stood next to a tractor under load, you expect a roar, but the engineers in Marktoberdorf collaborated with MAN to rewrite that expectation. They utilized a 12.4-liter, 6-cylinder MAN D2676 engine, a unit originally designed for commercial trucks, and adapted it specifically for the agonizing, fluctuating torque loads of deep tillage. The goal was to force the engine to operate within a strictly narrow range of 650 to 1700 RPM. This wasn't just about quieting the cabin, it was a mechanical strategy to extend engine life and maximize fuel efficiency by drastically reducing the number of revolutions required to generate power. The result of this engineering philosophy is a machine that delivers 2,400 Newton-meters of torque at just 1,100 RPM in the flagship Fendt 1050 Virio. By modifying the engine mapping and turbocharging systems, they prioritize longevity over the high-revving peak power that characterizes so many competitors. It is a system that validates the premium price tag, not through flashy bodywork, but through the physics of combustion. However, generating that power is only half the battle. Transferring it to the mud is where the real war is fought. This brought about the Virio drive transmission, a significant evolution from the original Virio gearboxes of the 90s. The new architecture featured 2 independent hydraulic motors, one dedicated to the rear axle and a separate one for the front. This separation allowed for variable torque distribution, meaning the tractor could sense traction loss and shift power between axles instantly. It also introduced a pull-in turn effect. During a tight corner, the front axle creates a pulling motion that reduces the turning radius by up to 10%. It is a feature that directly addresses the maneuverability issues that plague large tractors. Additionally, once the machine hits speeds above 25 km per hour, the front axle drive motor completely disengages, eliminating drag losses and boosting transport efficiency. Interestingly, this mastery of independent axle control didn't appear out of thin air. It was heavily influenced by the data gathered from the Tresix Virio project, that 6-wheeled 540 horsepower prototype that never saw mass production. While the Tresix was a commercial dead end, its experiments with high horsepower traction management provided the blueprint for the Vario drive system, proving that even Fendt's failures are often just research in disguise. Beyond the transmission, the 1000 Vario declared war on soil compaction through Vario Grip, a fully integrated tire pressure regulation system. While competitors viewed tires as static rubber rings, Fendt engineers saw them as variable components. The system allows operators to switch between field and road modes via the Vario terminal, inflating or deflating specifically designed tires in minutes, even while the tractor is moving. This dramatically increases the contact patch in the field to float over soft soil, then stiffens the sidewalls for stable road transport. The economic impact of this technology was validated by research conducted at the South Westphalia University of Applied Sciences. Data showed that optimized tire pressure resulted in a 10% increase in tractive power and an 8% increase in area coverage. Perhaps most critically for the bottom line, it led to an 8% reduction in diesel consumption per hectare. Over 5,000 hours of heavy draft work, these efficiencies translate to potential savings of 50,000 euros. Independent tests reinforce this supremacy. In the DLG Power Mix tests, the Fendt 1042 Vario achieved a record low diesel consumption of 235 grams per kilowatt hour, and a review by Profi magazine noted the 1050 Vario was nearly 20% more frugal than all previously tested tractors. As the mechanical hardware reached this peak of efficiency, the company began its pivot toward the digital ecosystem. The introduction of the Ideal Combine, a jet black harvester designed from a blank sheet, and the Fendt One digital cab signaled that the next frontier was data. Screens replaced buttons, and connectivity became as important as horsepower. With projects like the Xavit robot swarms, the company is already looking toward a future where the tractor itself might disappear, replaced by autonomous units. There is one final metric that silences the critics: the resale value. In the used market, a Fendt defies the normal laws of depreciation. It is not uncommon to see a 5-year-old Vario sell for 60 to 70% of its original purchase price, nearly double that of some competitors. Dealers often joke that the cheapest way to drive a tractor is to buy a new Fendt and sell it 3 years later. The high upfront cost is effectively a deposit that you get back when you hand over the keys. It turns the machine from a consumable expense into a liquid asset. But whether it is a 6-horsepower diesel Ross replacing a horse or a 500-horsepower Vario optimizing tire pressure, the mission is a relentless siege against waste. The Fendt tax is often debated in dealership offices, but for those who understand engineering, it isn't a surcharge. It is the cost of absolute precision. So, is that performance worth the premium? Well, let us know in the comments, and I'll see you on the next one.